In this video, we're going to continue our discussion of Taylor and Maclaurin series. Given the Maclaurin series of f of x is equal to e to the power of x, as e to the x is equal to summation n equals 0 to infinity x to the power of n divided by n factorial, in expanded form, we can write this as e to the x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4th divided by 4 factorial plus x to the 5 divided by 5 factorial. So t1 of x would be a polynomial of degree 1. That's going to be 1 plus x. t2 of x is a polynomial of degree 2. So we get 1 plus x is the sum of the first three terms. 1 plus x squared divided by 2 factorial. t3 of x is a polynomial of degree 3. So it's the sum of the first four terms. We get 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial. And t4 of x is the sum of the first 5 terms. So we go up to the x to the power of 4 term. So 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the 4 divided by 4 factorial. And similarly, t5 of x is a polynomial of degree 5. So we go up to the x to the 5 term. So that's the sum of the first 6 terms. So 1 plus x squared divided by 2 factorial plus x to the power of 3 divided by 3 factorial plus x to the power of 4 divided by 4 factorial plus x to the power of 5 divided by 5 factorial. So t1 of x, t2 of x, t3 of x, t4 of x, t5 of x are approximating polynomials. The higher the degree of tn of x, the closer the approximation to the function e to the x in this case. All right, so here we have a graph. We have the function e to the x, and you can see that we have t1 of x is equal to 1 plus x. That's basically the tangent line at x equals 0. And you can see it kind of follows the curve, but it's only tangent at one point. And it follows it fairly closely, but not closely enough. If you look at t2 of x, this is a quadratic polynomial, and the green curve follows e to the x much more closely, so it's a better approximation. Similarly, if we were to plot t3 of x, a cubic polynomial, t4 of x, t5 of x, we get a better approximation. That means we will follow the curve e to the x more closely. So we say that a function f of x is a sum of its Taylor series if f of x is equal to limit as n approaches infinity of tn of x. Let's define the error. The error is a difference between the function and the terminating polynomial, because if you have a polynomial of degree n, we terminate it at the power of n. So let's write tn of x. tn of x for the case of e to the x is going to be 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on, and we terminate at the x to the power of n term, x to the n divided by n factorial. So our goal is to have a measure for the error, the difference between the function e to the x and the approximating polynomial. And if we can show that the error approaches 0, then we can show that the function can be represented by this Taylor series. All right, so what we like to do is show that the limit as n approaches infinity of Rn of x is equal to 0. If we can show that, we have limit n approaches infinity of Rn of x. This is equal to limit as n approaches infinity f of x minus tn of x, and this is equal to 0. So let's solve for f of x. We get f of x is equal to limit as n approaches infinity of tn of x. So the step here was when you take the limit of the function, it's just going to be f of x because it doesn't depend on n. So we get f of x minus limit as n approaches infinity of tn of x is equal to 0, then swing this over to the other side, and we get this result. If we can show that the limit of Rn of x is equal to 0, then we have shown that the function f of x is equal to limit as n approaches infinity of Tn of x. So let's go over some theory. Assume that f of x is infinitely differentiable. That means we can take infinitely many derivatives on an open interval containing the center A. That means absolute value of x minus A is less than capital R. Capital R is a radius of convergence. If we can show that the limit as n approaches infinity of Rn of x is equal to 0 for all x in the interval of convergence, A minus R, comma A plus R, then f of x is equal to the sum of its Taylor series. So we always need to show that the remainder term, the error, approaches 0 as n approaches infinity. All right, so let's look at Taylor's inequality. If the n plus 1th derivative of the function, if the absolute value of this is bounded, so it's less than or equal to m, for absolute value of x minus a less than d. That means for the interval x between a plus d and a minus d in this interval of convergence, then the remainder Rn of x of the Taylor series satisfies this inequality. Absolute value of Rn of x is less than or equal to capital M. Recall, capital M is the upper bound for the n plus 1th derivative of x. So less than or equal to capital M times absolute value of x minus a to the power of n plus 1 divided by n plus 1 factorial. For absolute value of x minus a less than or equal to d. M is the maximum value of absolute value of fn plus 1 of x, the n plus 1th derivative of function on this interval a minus d, comma a plus d, on this interval of convergence. So if we can show that the limit as n approaches infinity of the remainder term is equal to 0, then we have proven that the function f of x is equal to the sum of its Taylor series. So let's do an example. We would like to show that the Maclaurin series for sine x is equal to x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial. So we have to kind of prove that the limit of the remainder term is equal to 0. Let's do that. So we would like to prove that sine x, the Taylor series of sine x, which is x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial minus x to the 7 divided by 7 factorial, converges to the function f of x is equal to sine x for all x. But to do that, we have to prove that the limit of the remainder term, the error part, approaches 0 as n approaches infinity. So let's start by taking some derivatives. And f of x is equal to sine x. F prime of x is equal to cosine x. F double prime of x is equal to negative sine x. And f triple prime of x is equal to minus cosine x. The fourth derivative, f4 of x, is going to be sine x. Now clearly, all the derivatives alternate between plus or minus sine x or plus or minus cosine x. So the nth plus 1, the n plus 1th derivative of the function is equal to either plus or minus sine x or plus or minus cos x. In either case, the absolute value of the n plus 1th derivative, evaluated at x, is going to be less than or equal to 1. Why is that? Because plus or minus sine x or plus or minus cos x, the biggest it can be, the absolute value would be less than 1. Cosine and sine can never exceed 1. So let's apply Taylor's inequality. So let's do that. Taylor's inequality. Absolute value of Rn of x is less than or equal to capital M times absolute value of x to the power of n plus 1 divided by n plus 1 factorial. Now, we showed that absolute value of m is less than or equal to 1. So we just get absolute value of x to the power of n plus 1 divided by n plus 1 factorial. Now, holding x fixed, so holding x fixed, and taking the limit as n approaches infinity, and n approaches infinity, we will see that the limit as n approaches infinity of absolute value of x to the power of n plus 1 divided by n plus 1 factorial is equal to 0. That means that we have proven the limit n approaches infinity of absolute value of Rn of x is equal to 0. Now we know that Rn of x is less than or equal to absolute value of Rn of x and larger or equal to minus absolute value of Rn of x. Let's take the limit of all sides, limit n approaches infinity, limit as n approaches infinity, and limit as n approaches infinity. And then we can apply the squeeze law. We prove that the absolute value, the limit of the absolute value of Rn of x is equal to 0 by applying Taylor's inequality. And on the left-hand side, we get minus 0, which is 0. So by squeeze law, let's write squeeze law. By squeeze law, the limit of limit n approaches infinity of Rn of x is equal to 0. So what we have proven is that sine x is equal to sum of its Maclaurin series. So the key to proving that a function is equal to the sum of its Maclaurin series or the sum of its Taylor series is to prove that the remainder term approaches 0 as n approaches infinity, because the remainder term represents the error. It's the difference between the function and the approximating polynomial. All right, thanks.